Hello, good morning.
Good morning.
Good
So
morning, sir.
how are you all? After Deepavali. How are you all? What's your total number, total count right now?
Sir, it's 32
তোমরা
officially, but
কোথায় দেখতে
at
পাচ্ছ?
present the
আমি
number
আমি
of
তো আমি
participants.
তো আমি তো নাম্বারটা আমার চোখে পড়ে না। কোন
Sir,
জায়গাটা
এই যে
নাম্বারটা?
participants list এর একদম টপে।
না আমার কাছে পাচ্ছি কিন্তু ফিগারটা না ওপরে আছে, নামগুলো পাচ্ছি কিন্তু I cannot get the count, the total
হ্যাঁ স্যার
count.
একদম
ও হ্যাঁ 18,
টপে
right,
দেখুন
right,
participants বলে
right,
ব্র্যাকেটে।
right, 18.
Yes, sir.
So almost half of the total count, right?
Yes, sir. Yes, sir.
Question is why? তো সবে শুরু হলো ইঞ্জিনিয়ারিং পড়া, এখনই এত অনীহা? Do you have any update regarding your regular classes, offline classes, etc.?
No, sir. Not till now.
No, not yet.
No, sir.
Anyway, I'm going to start.
Okay, sir.
Yeah, is it visible to you?
Yes, sir.
You can say. Okay,
Yes, sir.
right. So we stopped here in last class. Do you remember? We stopped here. You just check.
Yes, sir.
You just check. Okay. So very basic model and very fundamental circuit theory. We have not applied any circuit theory, just basic concept of circuit. These equations can be easily derived. And could you try to get some hard or soft copies of these books, this book and this book?
Yes, sir.
Okay. Probably we are going to start today from here, right?
Yes, sir.
Okay. So in the previous equations, you have got two quantities, and that is the meaning of them. One is representing impedance and another is the inverse of impedance, that is admittance. It is a kind of conductance. Actually, it is a kind of conductance, or rather, it is easy to understand in terms of conductance. That is, one is resistance, another is the reverse of resistance is conductance. Again, the same problem. Why it is so? Okay. So now you can write the two equations in the form of 7 and 8. Just some mathematical manipulations will lead us to very important conclusions. That is the beauty of the set of equations we are going to use to mathematically model a very crude type of transmission line. Why it is crude? Because the transmission line is not in a very sophisticated bed or platform. It is laid either in a mud, is underground, or overhead. It may be straight, maybe with some bends. So there is no sophistication in its laying. But when we are dealing with this, to find out its property, then the simple mathematical formulations are going to help you. So you take the derivative on both sides with respect to space. Space means here space is one dimensional because the wave is, or the electric or voltage or current, and the circuit or transmission line is varying along certain direction that is called Z. Are you fine with equation 10?
Yes, sir.
Okay. So I'm going to next equation. It is our choice. Let's consider y and z, their multiplication as the gamma square, because we want to use it for our purpose, for our purpose, and based on our known mathematical formulations. So hopefully you can understand that what kind of equation you are going to solve right now. Are you fine with this equation number 11?
Yes, sir.
And can you predict the solution of this equation based on your existing knowledge of mathematics or differential calculus? What kind of equation it is? Hello, anyone? This equation
It's a
represents,
differential equation of degree 2.
this equation represents,
Second order differential.
একটু জোরে আমি শুনতে পাচ্ছি না।
Second order differential. So
হ্যাঁ?
it's second order differential equation.
Right.
Second order differential equation.
That is very generic term, but you go one step ahead.
The Laplace equation.
One step ahead. Okay. Let's see the solution. Can you tell the solution of this one? Laplace and Poisson's equations will come later on, but fundamentally you should consider this as a different, quote unquote, you could not mention the real term of this equation. Okay, I'm going to the solution first. So one similar equation you can derive for current. That's fine. Both current and voltage, they are just synonymous and they are related with some parametric quantities. My question is, they represent Helmholtz equation or wave equation. Laplace, Poisson's, that will come under different conditions. So more general term is the Helmholtz equation or wave equation. So its solution is where gamma is the propagation constant. So this equation it represents the wave as a function of z, that is a function of space. And where gamma represents the propagation constant, and gamma is equal to square root of impedance and admittance multiplied form. Remember, this is very important equation 13. Now we come to the solutions. Question is, you all know the solution, but what is the significance of two different terms? Do you have any idea? That why we write this general solution in this form? We have been taught, আমাদের শেখানো হয়েছে যে এরকম ইকুয়েশন থাকলে পরে এর সলিউশনটা এরকম হয়। But what is the physics behind this? Do you have any idea? Anyone from you? Anyone from you? I cannot hear you.
No, sir.
Sir, it represents the propagation of wave in both direction.
Who are you? Who are you?
So, Swastik Kumar Ghosh, sir.
Swastik. Swastik, you please. Just 1 minute. This big noise. Well, you're right that it means like that. Interestingly, the mathematicians, they found the solution, or the physicists, they found the solution, they don't know. But in reality, what happens we'll see later. Okay. So there may be 3 cases. When you are going
Okay,
to
sir.
solve one equation, here you are going to get 3 different cases. One, only forward moving wave will be there. or backward moving, that is the reverse moving wave will be there, or waves propagating on both directions, that is both positive and negative z, forward and backward waves will be there. Very wise solution it is, and I will show you. Maybe today, but let's see. So for current, we are going to have almost similar expression. Are you keeping the note in a proper way?
Yes, sir.
Please do it, otherwise you will face a problem. So now from earlier derivation in 7, you just check what was in 7. We are going to get equation 16. We are putting the value of Z, Vz from 14. So our ultimate aim is to get some interesting parameters. And I'm very sure that when Heaviside did this work, he had to go to different varying paths to land the final form. He did not know about which one is the right one to reach the solution. Now you can realize that what are the different forms. So it is just the substitution, and after substitution we are going to get the solution for current in terms of voltage, but in the form of wave. So now we are going to solve this as a function of wave. So initially we started just as current and voltage and their variation over the small length z or delta z. And just after crossing few steps, you are dealing with current and voltage in the form of wave as a function of z. Now we are taking help from 13. Are you okay with this? So we are going to introduce one interesting parameter Z0. And very soon you will find what important parameter it is. Equation 18 is very important equation where current is expressed in terms of voltages. Forward moving voltage and backward moving voltage. So when you get this equation 18, now you give some attention to this parameter Z0. Z0 is actually impedance parameter. You look at its dimension, it is actually impedance, and it is called characteristic impedance of the line. Why it is so? It is the characteristic impedance of the line. Wait, so we'll find its characteristics and then we can find why it is called the characteristic impedance of the line. When the line is set, line is fixed, then the impedance is settled. So it is not the function of other things, it is absolutely the inherent parameter of the line. Line এর কিছু জিনিস চেঞ্জ করলে পরে its characteristic impedance will be automatically different or changed. Note it from the very basic consideration, just put the value of the expressions and then you'll find z naught equal to the square root of these two parameters. Are you done up to 19?
Yes, sir.
Okay.
Sir, sir,
Yes,
I have a sir.
Sure. Ask question. Ask question.
Sir, বলছি sir in question 18
বাংলায়,
is there is
বাংলায়,
extra
যদি
v
কিছু
naught minus
কষ্ট-
like v naught by z naught?
just wait.
Sir বলছিলাম
হ্যাঁ, বলো।
equation 18
হ্যাঁ, বলো।
স্যার ইকুয়েশন 18 এ কি একটা v naught minus যেটা সেটা কি এক্সট্রা আছে একটা, কেন v naught by z naught into v naught minus
right. You are
equation
right.
18 টা?
You are right. Absolutely. Just wait. Do you use this math type? কি বলছে এখন আপগ্রেড করতে বলছে। Do you use math type? জানো
No,
না
sir.
তোমরা, ইউজ করো না। Okay. Thank you for কপি পেস্ট করতে করতে এই প্রবলেম গুলো হয়ে যায়। Thank you. Fine. Okay. So up to 19 is fine, right?
Yes, sir.
Yes sir.
Okay, I'm going to next slide. You note this thing or you can write this thing. There's two parameters, gamma and z, are extremely useful. Ultimately, at the end of the day, we will forget the procedure we derived, but what's our net outcome? Our net outcome is some inferences based on these equations. এই ইকুয়েশনগুলো ডিরাইভ করা মুখস্থ করার কোনো মানে হয় না, বিকজ ইট ইজ অল ডকুমেন্টেড ইন টেক্সট আফটার সো মেনি ইয়ার্স, সো পিপল নো হাউ টু ডিরাইভ। রাইট নাও you are getting this flavor that what is the steps or what are the steps behind this, but we are mostly interested as engineers to use its outcome or inferences or the information we are going to get. So gamma and z naught, that is characteristic impedance, they're very important. For any electrical engineer, he or she may be in electronics, maybe in communication, wherever it is, because when you are dealing with some electromagnetic wave, even in the devices, because most of the devices are for high frequency applications. So once the device is producing some signal, immediately you need to consider how you are going to collect the signal, trap the signal in your circuit. So everywhere it is required. So note this parameter is very important. One is gamma. Up to 21, all steps are important. And this is my derivation. You are not getting any from any book, this type of steps and derivations. For your quick understanding, logical understanding, I have prepared this steps. Should I proceed?
Sir, 1 minute, sir. We are just
Okay.
copying
Sir,
it.
please wait for 2 minutes.
Do it. There is a special thought behind this. This means the organization of this equation in this format. You'll find it soon. Well, do you notice one term I have used? Therefore, their characterization under practical conditions of the RF domain are very important. For low frequency signal, that is 50 Hz signal or below 50 Hz signal or DC signal, we don't consider it in the form of this typical, well, if even it is in the form of wave, but right now we are getting out of this scenario very soon. Means our concern is RF because we are communication people. We are not dealing with the low frequency signal. Low frequency signal radiate করে না। Low frequency সিগন্যালের কোনো প্রয়োজনীয়তা our electronics engineering এ নেই, because electronics engineering is basically meant for wireless communication. এটুকু তোমরা বোঝো কি বোঝো না আমি জানি না। There is another part that is called instrumentation. We are not electronic engineer for instrumentation. We are electronic engineers for communication. So our whole concern, whole focus of our curricula, it is only RF, RF and RF, that is high frequency or radio frequency. Well, should I proceed?
Yes, sir.
Yes, sir.
So it is not for right now. We are all comfortable with RF, but I am talking about the person who was working in the late 18th century. It is 18th century? No, 19th century. 19th century, later part. He was working with telegraphic signal. Can anyone read it? আমার সঙ্গে কে কথা বলছিলে? কি ঐন্দ্রিলা কথা বলছিলে? Who was talking to me?
হ্যাঁ ম্যাম, হ্যাঁ স্যার,
The ঐন্দ্রিলা, okay.
হ্যাঁ স্যার।
ঐন্দ্রিলা, can you read it very clearly?
The telegraph signals basically contain electrical pulses. We can easily visualize them in time domain. Their frequency domain representation is quite different.
Wait. Do you justify the term, the first sentence, that it is electrical pulses? Why? Telegraph signals, because it is not a DC signal, right? The nature of the signal is
Yes,
1
sir.
and 0, 1 and 0. So very, very frequently they are changing their pattern. So the signal has some rising
sir.
edge, some falling edge, again rising edge, falling edge, rising end, falling edge. Like if it is 1 0 1 0 1 0, so it will be a nice pattern of make break, something like that. But any alphabet, I already told you, Indrila probably joined later, so you did not know. Are you in this class from the very beginning? Or you have joined just last 2 classes?
No, sir. I have missed first.
Yeah, you have
Last
missed
2 classes, sir.
first classes. Okay, so that's why you people don't know what I discussed earlier. Because this telegrapher's equation is based on these telegraph lines, and telegraph lines means it is two-in-wire line, that is 2-wire line, and this line is used to transmit electrical signal in the form of make and break, like pulses.
Okay, sir.
It hardly matters how quickly you change your 1 to 0 or 0 to 1. whatever be its pulse rate, it hardly matters because this is done by our fingers. আমরা যেরকম টাইপ করি keyboard, similar type of keyboard was there for the telegraphic signal for transmission. So our finger speed, our they used to call it as baud. Anyway, you don't know this is baud speed, that is the signal speeding. That is not important. Important is the signal shape. The signal shape is very sharp end going up and very sharp end going down. So any sharp edge means very fast change of very fast change of current
from one state
in
to
a
another.
circuit. In a circuit, right?
Current.
So we can easily visualize them in time domain, but we frequently or normally, তোমরা এখনো, because based on your general concept, you don't realize its actual scenario in the frequency domain. So high frequency components appear
Yes, sir.
significantly high in those signals. আমরা কি দেখি, আমরা মিররে আমাদের মুখ চোখগুলো দেখতে পাই, but the internal nature of this body যেদিন খুলে 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 কেউ দেখে তার সে অবাক হয়ে যাবে যে এর মধ্যে কি আছে, হাড় গোড় মাংস. So that is called the internal vision. So that internal vision you can see. That internal view you can see through this. I'm just showing. This is your time domain signal. If it is the time domain signal, suppose a very sharp rise and fall. It is just one example. It is like very close to delta function. But for a sharp signal like this, in frequency domain, you are going to get the entire domain of frequency
For a
band
longer
it is covered. So low frequency component যেমন আছে, the equal amount of very high frequency component is there. Question is why? Because we are not concerned about this middle part. We are concerned about the rising part and falling part. So during this rising part and falling part, your time or delta t is very small. And you know, how do you count your frequency? Frequency is the inverse of time. So over this domain over which it is rising from 0 to high or high to 0 within the short time. So during this short time, this variation, it corroborates 1 upon delta t. So if the delta t is tending to 0, then your frequency component is going to be infinity. That means very high. So high frequency components are our main concern, but not the low frequency component. Okay?
Yes, sir.
Therefore, we are going to add some new conditions. That is the practical case, the transmission line. So far, we did not apply any boundary condition or any special condition. We did not care about its frequency. It could be used for little bit low frequency, medium frequency, high frequency, but right now we are restricted our study for high frequency or RF signal. So our concern is high frequency and low loss. High frequency and low loss transmission line. That means its resistive component should be very small compared to what? You just note it. So how do you define this load? That is, it is this reactive component. R is very small compared to this omega L part. Why? Because when omega is very high, then omega L component is really very, very high. So compared to that, the resistance is very low. So R by omega L should be considered much, much less than 1. Similarly, G by omega C, they are very small compared to 1. And once you apply this condition to your previous equation, what was the equation number? 19 or 20? What was the last number? I cannot see.
Sir, 21.
21.
21.
Okay. So now you see, your 21, it reduces to what? Hello? Now you are going to simplify it by using Taylor series. Taylor series, you know, square root of 1 plus x. It is a quick recap for you. So if it is so, and if x is small, because what is x? X is here, R by omega L. You see, R by omega L. So if x is small, then only the first term is sufficient, but the higher terms are negligibly small. So it is approximately close to this. And following this relation, your equation 22 helps you to reach simplified form of this one. Do you get my point? So 23 is the important relation for you to find out gamma. Gamma is the propagation constant. Very important for us because we want to find out some intrinsic or inherent property of the line in terms of gamma and Z naught. So first we see gamma. Gammaর মধ্যে দুটো component আছে, you know. Gamma is the propagation constant. So the propagation gives you two parameters. One is its phase, another is its magnitude in terms of attenuation. That is how quickly it attenuates. Another is what kind of change of phase it is going to have. Thus, we can find out these two parameters separately. Beta is equal to Are you familiar with this relation, the very simple relation? Are you familiar with phase velocity? Yes or no? Hello.
Yes, sir.
I'm asking all of you, have you clear vision about phase velocity and group velocity?
No, sir.
No. So no is more or yes is more? Well, I'm going to tell you, you have received my second slot invitation by WebEx. So you'll have to join it, right?
Yes, sir.
সবাই পেয়েছো? হ্যাঁ, কারণ 5 মিনিটের মধ্যে শেষ হয়ে যাবে। তোমরা নোটিফিকেশনটা তোমাদের কাছে গেছে যে 5 মিনিটের মধ্যে
Yes, sir.
শেষ হবে? হ্যাঁ, সুতরাং এটা কেটে গেলে পরে আমি আবার ঢুকবো।
না স্যার, ওটা আসেনি।
আসেনি, তুমি দেখতে পাচ্ছ
না,
আমার
স্যার।
এখানে এসছে।
স্যার
আমার
ওটা
এখানে
শুধু
এসছে।
হোস্টের কাছে আসে।
হ্যাঁ
ঘোস্টের
স্যার,
কাছে
ওটা
আছে?
শুধু হোস্টের কাছেই যাবে।
হোস্ট না ঘোস্ট?
হ্যাঁ স্যার,
হোস্টের
শুধু 5 মিনিট আগে
স্যার, হোস্ট
হোস্ট।
হোস্ট
ও।
হোস্ট
ও আচ্ছা, ঠিক আছে। তো নাও তাহলে ফেজ ভেলোসিটির সঙ্গে গ্রুপ ভেলোসিটি গুলিয়ে যায় কারো কারো নাকি? আচ্ছা, তা আপাতত আমরা ফেজ ভেলোসিটিটাই ধরে রাখি। এগুলো না ক্লাস না হলে এগুলো কেউ কাউকে দেখতে পাচ্ছি না, কিছু বলাও যায় না, মুখও দেখা যায় না, কি যে বলবো। তুমি যে
স্যার আমাদের কি 16 থেকে
এক
অনলাইন
মিনিট, আমি আমি
অফলাইন
আমি
ক্লাসে
আমি আমি আমি
স্টার্ট
আমি
হবে?
জানি না, আমাকে আমাকে পড়াতে বললে পড়াই, ইউনিভার্সিটি আর অন্য কোনো কাজের সঙ্গে আমার যোগাযোগ নেই, ওটা ইউনিভার্সিটি কর্তারা বলতে পারবে। আচ্ছা, তোমরা যে পা ফেলে
আচ্ছা,
হাঁটো, that is very similar to or identical to phase velocity. এক একজন মানুষ এক রকম ভাবে হাঁটে, তার ভেলোসিটিও সেরকম, ফেজ ভেলোসিটিও সেরকম। হোয়াট ইজ গ্রুপ ভেলোসিটি? সো হোপফুলি উইল গেট টাইম, আমাদের এই কারিকুলামের মধ্যেই আসবে, সো উইল ডিসকাস ইট, গ্রুপ ভেলোসিটি এন্ড ফেজ ভেলোসিটি ডিফারেন্সেস। বইতে অনেক কিছু লেখা থাকে কিন্তু বসে বোঝা যায় না, সো I will give you the physical interpretation. So right now it is phase velocity, you know, and relation of beta. Well, I'm quitting now and I'm joining again.
okay, sir.
Okay, sir.
Quitting now. Well, is it visible to you?
Yes, sir.
Okay. So this relation with beta omega relation, that you can get from equation 24 or 25, their identity. And definitely they are going to give you about the attenuation constant alpha. This is your attenuation constant. But you just note few things. It is going to give you two information. One is loss in insulator. It is called conduction loss, and loss in conductor, sorry. Attenuation. It is actually the leakage, the loss through insulator, and it is the conduction current that is through R. So these two losses are the main losses for attenuation. This is called dielectric loss. and this is called conductor loss or ohmic loss.
স্যার হ্যালো
হ্যাঁ বলো।
স্যার এটা লস কি করে বলছে আর কি
আচ্ছা বেশ, তা কি হতে পারে? This factor, it is coming from propagation. This factor gives you two parameters. One is containing R, another is containing G. When you are applying current through these two different quantities, এই দুটো কোয়ান্টিটির মধ্যে দিয়ে যদি কখনো কারেন্ট যায় কি হবে বলো? আর এর মধ্যে দিয়ে কারেন্ট গেলে কি হয়? আর এর মধ্যে দিয়ে কারেন্ট গেলে কি হয়?
হিট জেনারেট করবে ও আচ্ছা
তাহলে একটা হবে হিট জেনারেট করবে, আরেকটা হচ্ছে ডাইইলেকট্রিকের মধ্যে দিয়ে কারেন্ট গেলে কি হয়? ডাইইলেকট্রিকের মধ্যে দিয়ে কারেন্ট গেলে কি হয়? সেটা তুমি জানো না। Well, I'm helping you. If a dielectric is exposed to electromagnetic wave, তাহলে কি হয়? একটা ডাইইলেকট্রিক একটা ইলেকট্রোম্যাগনেটিক ওয়েভের মধ্যে দিয়ে বসিয়ে রাখলাম, তাতে কি হবে তুমি জানো?
হ্যাঁ
কি হয়?
সেটাও তো ম্যাগনেটাইজড না সেটা
ম্যাগনেটাইজড হয় না। তোমার সিঙ্গারা ম্যাগনেটাইজড হয়? প্যাটিস ম্যাগনেটাইজড হয়? কি হয়? কি হয়?
গরম হয় গরম হয়
হ্যাঁ, চা দুধ কফি মাইক্রোওয়েভ ওভেনে ঢোকালে কি হয়?
গরম হয়
গরম হয়। Actually it is called dielectric loss. Depending on the dielectric constant, it has two. Dielectric constant has two components. One is the real and another is imaginary. So imaginary part gives you the lossy part.
আচ্ছা
That imaginary part gives you the facility of getting it heated. Fortunately সেই জন্যই তুমি মাইক্রো ওভেনটা ব্যবহার করে বাড়িতে গরম গরম খাবার খেতে পারো।
হ্যাঁ হ্যাঁ
You use biscuit and 1 cup of tea. কোনটা গরম হয় ভালো? একই সঙ্গে ঢুকিয়ে দিলে পরে
টিটাই হবে
টিটা হবে, because জলের ডাইলেকট্রিক কনস্ট্যান্ট লসি পার্ট is much higher than that of simple biscuit.
হ্যাঁ
বিস্কিটের মধ্যে মেইনলি আটা বা ময়দা,
হ্যাঁ
they are not lossy at all. So সেটা হচ্ছে তুমি আরএফ দিয়ে দেখলে। Similarly, if current, if you allowed to pass through some dielectric, যখন আমরা বলি লিকেজ কারেন্ট, খুব খারাপ অবস্থা হয় বাড়িতে, লিকেজ কারেন্ট যদি যায়, এটা শর্ট করে দেয় এবং সিস্টেমটাকে নষ্ট করে দেয়। তো অনেকের বাড়িতেই দেখবে মাঝে মাঝে দুমদাম এটা ওটা উড়ে যাচ্ছে, তো বিকজ অফ দিস লিকেজ কারেন্ট। So they are going to give you the loss condition, but we don't want it to be lossy. A low loss condition এর জন্য we can apply the same high frequency low loss condition to this one. Anyway, so this is really for attenuation. We are apply this condition to Z naught. Z naught is equal to is your characteristic impedance. This characteristic impedance, we are going to manipulate it little bit in this form. Then you can realize it is helping you to make it smarter. How? You do this manipulation. Once you do this manipulation, you are getting this equation like this. So you just consider this first term. It is giving you just one, because they are negligibly small. They are negligibly small compared to 1. So 1 by 1 it is 1, and you are getting its value square root of L by C. Well, can you do some dimension analysis to check the unit of Z naught? L by C দিয়ে তোমরা করতে পারবে চট করে? Can you check an impedance unit, is it coming correct or not? You do this homework. You know unit of L, you know unit of C. Put these values and you will find that the square root of L by C is giving you simple V by I, or impedance parameter or unit. So now we see the next one. That is very important. আমরা তো দেখলাম it is high frequency. When it is at high frequency, then your transmission line gives you these parameters. Is it true when you are coming close to zero or in between zero to infinity? High frequency, mathematically I am considering it infinity. But actually it is not infinity, it is actually compared to zero frequency, means DC frequency. When the frequency is sufficiently high, then it is applicable. Suppose it is VHF. Suppose it is HF. But if it is very low frequency or medium wave frequency, then this relation may not be valid. So when it is close to zero or DC, what kind of change we are going to have? So we go back to 20. This is the more general equation where we did not apply any condition of high frequency or low loss. We can write alpha and beta in this form. This is just very simple steps of mathematics. Question is when it is f equal to 0. Can you find out when f equal to 0 what is the value of alpha and beta? Is it okay? Alpha square root of Rg. And when f equal to 0, the beta equal to 0. That means no propagation takes place. So this is the terminal condition when we are at one end. It is f naught. The marginal condition alpha and beta is like this. Now just you see. One is alpha versus omega, another is beta versus omega curve. This is the value when omega equal to 0. And this is the value when omega is equal to infinity. When omega to infinity, what is the value of alpha? This is the value of alpha. Are you getting my point?
Yes, sir.
Yes, sir.
So we are showing you the two conditions or two extreme condition when এখানে আমি দাগটা দিতে পারছি না because of some technical problem. So suppose it is square root of Rg when omega equal to 0 and when omega is equal to infinity, so this is the line. Here when omega equal to 0, beta equal to 0, and when omega beta it is the high frequency, it follows this relation. Question is when it is close to this frequency, এইখানে যখন থাকবে বা এটা যখন এই অঞ্চলে থাকবে, this value is not true. এই ভ্যালুটা ঠিক নয়. This value is true for high frequency. This curve is true for high frequency. So what is the actual thing? I have drawn two imaginary lines here, which is valid for high frequency, not for low frequency. You see what is the changes in low frequency. It gradually বাড়তে থাকে. It grows gradually. And at high frequencies, that is asymptotically, it's close to this value. So this is the curvature. So when we are close to or near cutoff, or if not, then the value changes. Here also, this curve is like this, but when you are close to this, that they don't follow, or it does not follow the straight line. Rather, it takes the nature of this curvature and gradually comes to zero value. So this is the practical nature of the curve. But interestingly, as communication engineer, we are not concerned with the low frequency part. So low frequency part is not for us. It is for the other engineers, and they need it. So for us, this equation is valid for high frequency, and this equation is valid for high frequency approximation. So let's proceed. A comment. I'm giving you one interesting condition. So you note it down. What was the ultimate aim of Heaviside? To minimize the distortion, to know the reason of distortion and how to control the distortion. So all frequency components get attenuated by equal amount, then your attenuation, then your distortion will be minimal. And all components travel with same velocity. That means this is the indication of dispersion or non-dispersion. Dispersion means in a medium when different components of frequency, different components of signals, that is frequencies of signals, they don't travel at the same velocity, then it is called dispersive medium. And dispersive medium is actually reducing distortion. So you can try. মাঝে মাঝে এটা কি করে আর কি। So you can try this condition. R by L equal to G by C, then you can find that it is going to give you a beautiful solution. Okay, so this is the last slide for module 1. Now let me share the different one. Can you see that now? Can you see?
No, sir.
You cannot see right now, right? Okay, just a minute. Just a minute, again a problem. Okay. I think it is visible now.
Yes, sir.
Yeah.
Yes,
Okay,
sir.
better. Okay. And that is the main goal of a technical person who is dealing with either any transmission line or for any communication. That means my target is to reach the termination or the terminal point. And it depends on the matching. What kind of matching? Let's see that part. And Heaviside first told that the matching is one important parameter, one important part for transmission line. And later on, there are several scientists, they work on the matching device, matching circuits. Carl Ferdinand Braun, he was a Nobel laureate with Marconi. Braun was German scientist, and if you're familiar with cathode ray tube or cathode ray oscilloscope, so he was the inventor of that one. And Carl Braun was the pioneer in understanding and focusing on the matching device and matching network, matching circuits. Matching means in terms of impedance matching. I'm coming to that part. Well, the photograph shows you the situation that when one electromagnetic wave comes and falls on a medium, on a body, what are the possible phenomena? One is a few part or the 100% of the incident energy will be transmitted through this medium. চলে যাবে ভেতর দিয়ে। And that is the most expected situation. But unfortunately, the real world does not show this type of feature. Why? Because that 100% perfection in any system is typically impossible. So a part is reflected from this medium. So what happens? One is transmission, another is reflection at the point of incidence. Now we look at similar example or similar phenomenon in case of a transmission line. Suppose the transmission line is a speaker and this is your music system. And this music system is connected through a pair of transmission lines to the speakers. What do you expect? That what amount of power is being generated and audio signal? So that audio signal should go to the speaker 100%. So this is the situation that you are expecting the transmitted wave fully going to the ZL, that is your load. your speaker is actually a load. Do you know what is the specification of a speaker? Loudspeaker specification কি হয় বাজারে গিয়ে কি বলতে হয়? Do you have any idea? Have you ever seen any loudspeaker
Yes, sir.
touching on your hand? কি লেখা থাকে স্পিকারের গায়ে দেখেছো কোনোদিন? জানো না, না? Can you guess? Any intelligent one can guess because I already mentioned that your speaker is a load. So what should be the specification of a load? Load means load impedance. What is the unit of impedance? What is the unit of resistance?
Ohm, sir.
Oh,
Pronounce কিভাবে pronounce করলে শুনি একবার? You pronounce it properly? It is not ohm.
oh,
Ohm.
It is after the name of George Ohm. H-টা silent থাকবে। হালকা উচ্চারণ হবে। এটা যে জার্মান হয়তো আমরা সঠিকভাবে উচ্চারণ করতে পারি না। ওম। তাহলে ইম্পিডেন্সের ইউনিট কি হবে? ওম। আর স্পিকারের স্পেসিফিকেশন কি হবে? দ্যাট ইজ অলসো ওম। এই যে স্পিকারগুলো তুমি ইউজ করো, এগুলো গায়ে দেখবে লেখা আছে 8 ohm স্পিকার। দ্যাট ইজ the load is 8 ohm. Sometimes it is 4 ohm. লো ইম্পিডেন্স স্পিকারও হয়। যখন ল্যাবে আসবে, just remind me. I will show you some practical speakers and their specifications.
Yes, sir.
যদি এই ম্যাচিংটা না হয় কোনো কারণে, the impedance is not matched with your transmission system or line, then the odd situation will happen and you will not be happy. The most of the power will be reflected back. So power, when it is reflected back, it is not going to affect only the less power in the speaker, but it is creating some another issue in the line. So that is the main part.
Sir,
Yeah, please.
স্যার বলছিলাম, স্যার ম্যাচিং বোঝাচ্ছে যে আমার যে স্পেসিফিকেশনটা লোডে লেখা রয়েছে সেই অ্যামাউন্ট অফ পাওয়ার অথবা এনার্জি সেখানে যাচ্ছে কিনা।
ম্যাচিং মানে হচ্ছে বোঝাবুঝি, মিউচুয়াল আন্ডারস্ট্যান্ডিং। এই মিউচুয়াল আন্ডারস্ট্যান্ডিংটা ইলেকট্রিক্যাল প্যারামিটার যখন দেখবো, এখন সেটা তুমি বুঝতে পারবে। এখন বুঝতে পারবে তুই কি করে ম্যাচিংটাকে ধরবে। ম্যাচিং মানে হচ্ছে মিসম্যাচটা কম হবে। সংসারে যেটা সব থেকে বেশি হয়, বাবা ছেলের কথা বোঝে না, ছেলে বাবার কথা বোঝে না, মা মেয়ের কথা বোঝে না, generation gap. So that is not expected in case of transmission line. So engineers are always very careful to match at every point. Otherwise, the very precious power, high frequency, that is lost, and that is not at all expected. Okay. So now we go to
ওকে স্যার।
that part. How to estimate the matching? So again, we are coming to the basic configuration of a transmission line. You can draw it again. Where we are going, we will have two additional parameters, that is VS, we call it source voltage. and VL, that is the load voltage. IL is the load current. IS is the source current. So the RF source is connected at the source point, and one impedance is connected at the load point, that is the another port. So one is port 1, we call input port, and another is the another port 2, that is called the output port. So this transmission line is typically of this type of transmission line. We have two ports, input and output, so it is a two-port device. Z is an arbitrary distance and total length of the line is L. And what is here, you see there are two parameters at the input. One is ZS, that's the source impedance. And another is Zin. Zin is the input impedance. That means what impedance I am seeing from the input end. Very important parameter is Zin. That is current voltage relation at the input end that determines what is my Zin. So quickly, we again take, but we'll go to the new sets of equations from 14 and 15. So we're going to use some old equations for our new derivations. So now these two equations, we call it 1 and 2. I would request you to repeat these equations again on your exercise book and write them as 1 and 2. Because we'll use it to find out some relation, and for that we'll use two different conditions. One is input condition and the output condition. For input, Z equal to 0. So obviously we call it V at input terminal Vs and I at input terminal Is, source current and source voltage. So from 1 and 2, can we write? Do you agree? Because just put Z equal
Yes,
to
sir.
0, Z equal to 0, and for when Z equal to 0, V equal to Vs, I equal to Is. So this is our new set of equations 3 and 4, which help expressing voltage as, that is our intention, that is from V 3 and 4, we can write this equation. এই V0 টা আমাদের কাছে হেজি ছিল, রাইট? আমরা জানতাম না V0 টা কি। But we know about our transmission line. So transmission line parameters গুলোকে জড়াতে হবে V0 and V plus and V minus এর সঙ্গে। এগুলো জাস্ট কতগুলো symbolic parameter ছিল। So we are gradually now entering into some realistic parameter. দেখতে পাবে যে কি বিউটিফুল ওয়েতে আমরা একটা ম্যাথমেটিক্যাল পার্ট থেকে একটা ফিজিক্যাল পার্টে ঢুকে যাব। So this mathematical part is 5 and 6. It is little bit physical now. So our input part is over. We are going to the output, that is load end. Load end এর জন্য Z কত বসাতে হবে? What is the value of Z now?
L.
L. So now our task is not that easy what we had in case of Z equal to 0. Not a problem. So in that case, we will define VL as this and IL, or Z not IL, in this form. So we will repeat similar expression. Now you can find that same parameter can be expressed in two different ways. And when you use it by using these types of equation, we'll get some additional benefits. Should I proceed?
Yes, sir.
Okay. I'm going to get this to 7 and 8. So you had different equations. Now you have two different equations. Now can you realize that we are going to the real world gradually? All real quantities right now. So these sets of equations help us deriving some useful combinations. Just a minute. এখন দেশে চলে যাচ্ছ? তোমাকে টাকা কখন দিতে হবে? এখন তো আমি ক্লাসে আছি, আমি তো এখন দিতে পারবো, ক্লাস শেষ করে দিতে পারবো। আর তুমি 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 দেখো, আমি তোমাকে একসঙ্গে এখন তোকে দেবো না, আমি তোমাকে 10 মতো পাঠিয়ে দিচ্ছি। আমাকে হ্যাঁ আমাকে আমাকে তোমার 45 মিনিট সময় লাগবে। হুম। The purpose, now it is clear to you what is our purpose of identifying Vs and Is. That means I want to see what is my input impedance. So once this equation is done, 9, I will put the values of V naught, all V naught values in terms of the real physical parameter what you already have got, the form of 7 and 8. That means our interest is to find out the matching. So now we are saying what are the quantities. One input impedance, one is the output impedance. It is not yet visible, but it will be visible very soon. And another is the characteristic impedance of the transmission line. Okay, so let's proceed with few steps. When you were writing the second line, after After that, we will apply this relations of sine hyperbolic and cosine hyperbolics. So it is transforming to the last equation. Are you done?
No, sir.
Okay, do it carefully. And you will see our ultimate game, ultimate aim, ultimate utility is not with VL or IL or anything. It is the impedance, because matching will be controlled, will be governed by the impedance parameters. And only 3 parameters are important: input side, output side, and the line parameter, that is the line impedance. Line impedance means characteristic impedance. Are you done?
Yes, sir.
What about others?
Yes, sir.
Okay. ZL এতক্ষণ ছিল না. Now we have converted that VL and IL to ZL. This is a very fine equation, but not the finest one. So we need to proceed a few steps to reach the usable equation. What's that? Tan hyperbolic with argument j, that is the complex number beta L, then it is equal to j of tan beta L. So we are writing it in this form. And this is the equation which has to be memorized. And this is like the most common, it is like the most common medicine, Calpol. মানে কথায় কথায় তোমার এটা কাজে লাগবে। সো চোখ বন্ধ করলেই এই ইকুয়েশনটা দেখতে পেতে হবে, অর ইউ নিড টু রাইট ইট ইনস্ট্যান্টলি। কেউ তোমাকে এটা প্রোভাইড করলো বা না করলো, it hardly matters. So there are few relations which are like V equal to IR. So no, you need not any reference for this. So like line impedance or input impedance. So input impedance is equal to this. Now you can see here that Z in divided by Z naught and yeah, it is all right, because the numerator denominator, it is unitless quantity. Okay, so it is Z in Z naught. It's okay, fine. So one of the major lifetime equation, yeah, it is required for your whole life. And many of these relations and equations are equally important for your GATE examination and solving multiple problems. If you are done up to 10, then I can go to next step. Are you done?
Yes, sir.
Yes, sir.
Okay. বলো তো কোন কন্ডিশন অফ লোডে রাইট সাইডটা 1 হয়ে যাবে? right hand side will become 1 under a very special condition of the load. Which condition?
The Z naught equals to ZL.
Z naught equal to ZL. তার মানে লোড ইম্পিডেন্স যদি লাইন ইম্পিডেন্সের সঙ্গে এক হয়, then your right hand side will be 1. And what is your inference will be there? So many more situations will be examined in the future. There are many more situations will be like this. Then you can understand this one. But I already mentioned that reflection is a part of the system. তার মানে ZL or Z naught, a perfect matching, it's very difficult. So the practical situation is there will be some reflected signal and some based on some incident signal. And if we can account for this, then we can easily determine what is its nature of reflection. So reflected voltage and incident voltage, and mathematically reflection voltage based on your equation, you can write it straightforward, reflection coefficient as V minus by V plus. And again, V naught can get from 7 and 8. So the equation takes this form. And finally, it is very simple. And not only that, it is simpler. ZL minus Z0 by ZL plus Z0. Very important relation. This reflection coefficient depends on the load condition. তোমাকে একটু আগে দেখলে তুমি লোডের সঙ্গে যদি Z0 এক হয়ে যায়, then there will be the right hand side will be 1, and in that case Z in will become Z0. Why it is so? Again, the material will be completed within 5 minutes. Okay. Once the meeting is complete, I will send one more link.
Okay, sir.
So equation 11, you look at 11 equation. If ZL equal to Z0, your reflection coefficient will become কত হবে? Reflection coefficient কত হবে?
0, sir.
0. That is the ideal situation.
Zero.
এই এতক্ষণে তুমি বুঝতে পারলে যে আমার আইডিয়াল সিচুয়েশনটা হচ্ছে যখন আমার load will become Z0 equal to Z0, and under this condition my input impedance will become the characteristic impedance. So that is the most desired situation, that the line impedance should be matched with both input impedance and output impedance. এই কন্ডিশনটি করতে পারলেই তোমার you are getting the ideal situation, ideal engineering situation for application.
স্যার তখন কোনো ভোল্টেজ রিফ্লেকশন হবে না যখন আমার ক্যারেক্টারিস্টিক ইম্পিডেন্সটা লাইন ইম্পিডেন্সের সাথে ম্যাচ করে যাবে।
Absolutely, absolutely. If it is a natural thing. When it happens, then there will be no reflection. পরে কথা বলছি। Okay.
Yes, sir.
So we are going to. Oh, further, it is very important for you to remember the reflection coefficient is a phasor, the complex term. Because Z is a complex term, but Z naught is a complex term. ZL Maybe complex, maybe real, but z naught is always real. তোমরা দেখেছো z naught is equal to square root of L by C. So there is no scope of having its imaginary part. Well, later on. পরে. Hello.
Yes, sir.
Okay. And this is also true. Its value will be either 0. Hello? Yeah, I'm in a
Yes,
class.
sir.
So its maximum value will be 0 and maximum value will be 1. When it will be 1, there will be no transmission. So it varies between 0 and 1. Probably I should send a different link right now. I'm quitting now.
Okay, sir.
কতজন ছিলে তোমরা?
Sir, 24.
আমাকে নিয়ে বাদ দিয়ে।
না, আপনাকে নিয়ে 20.
It is out of
32.
very alarming. Very alarming. It's visible, right?
Yes.
Yeah.
Yes, sir.
Okay. So reflection coefficient at any point Z. So our intention was to find out this matching of the transmission line. So we'll examine various conditions so that you can understand what is our ideal situation, what is to be avoided, what is the most worst type of condition. So we do this exercise. So you get a point that this is Z. If it is the total length, there is one length is L primed on the other side. So Z plus L prime is giving you the total length. Okay. So you just simplify this equation. And now you're having this relation 12. What was rho actually? Rho টা কি ছিল মনে আছে? Can you go to rho?
So reflection coefficient.
No, rho is the reflection coefficient. Okay. Reflection coefficient. Okay. Reflection coefficient to attend. Okay. 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 So this is the expression of ZL minus Z0 plus ZL plus Z0, and along with this, for any value, you can find its value like this. And for small derivation or not derivation, for small quick problems for calculation, I just show you one small example that if the incident power is P in, the reflected power is equal to P minus by Z0. The incident and reflected power, then the reflected power is related to the reflection coefficient. And this is the total rho square into total incident power. It is quite obvious because reflected voltage is related to rho, that is reflected voltage and incident voltage. So their square, it is just the square, that is the power, the square of voltage, the square of reflection coefficient. So it is just the square term of its magnitude, and you can determine the reflected power from incident power. To give you reflection coefficient. As an engineer, you will get only the impedance parameters from the specification. So from this impedance parameter, you need to determine what is my reflection coefficient. And if it is the reflection coefficient, that what amount of power is transmitted and what amount of power is reflected back from your total incident power, you can easily calculate. So if you are fine with this, I'm going to next slide. What is the manifestation of reflection? Manifestation of reflection means when there will be reflected wave, it is associated with some forward will be present. And you can very easily visualize the situation. The left to right, that is source to load, and reflected from load to source. You just look at. One by one, you look at, first you look at the blue one. Blue one is left to right. Red one is right to left. So one is forward moving wave. Another is backward moving wave, that is the outcome of reflection. And when both are present, you look at the bottom, this wave is as if it is standing. It is standing and dancing. That is the net outcome when both waves are present in a line. And this is called standing wave. Physically, you can visualize that how the standing wave is formed. That is the most unexpected situation in a transmission line. We don't want any kind of standing wave. But standing wave we cannot avoid, but it has to be as minimum as possible. That means when my reflected signal, the red signal is low, but forward moving signal definitely it is high, then the standing wave pattern, the standing wave ratio, standing wave itself will be weak. So we always want weak standing wave. Gradually we are coming to standing wave ratio later on. Oh my God. গৌরাঙ্গ, এর নাম কি? গৌরাঙ্গই তো নাকি?
ইয়েস স্যার।
তোমার কি হয়েছিল বাবা, এতক্ষণ লাগলো কেন ঢুকতে?
স্যার অ্যাকচুয়ালি আমি একটু স্বাস্থ্যসাথীর জন্য ফটো তুলতে গেছিলাম।
তুমি কি এই প্রথম ঢুকলে ক্লাসে?
না না, আমি আগের ওয়েবএক্স এর আগে দুইটা মিটিং অ্যাটেন্ড করছি, কিন্তু গুগল মিটটা অ্যাটেন্ড করলাম এখন।
ও কালকে মানে আগেরটা করেছো, আজকে এই প্রথম ঢুকলে?
না না, আমি আজকে সকালে দুইটা মিটিং ছিল ওয়েবএক্স এ, ওই দুইটা অ্যাটেন্ড করছি, কিন্তু গুগল মিটেরটা এখন ঢুকলাম।
তো এর মধ্যে তোমার হয়ে গেল ছবি তোলা?
হ্যাঁ, লাইনে দাঁড়ায় ছিল মা, আমি এখন গেলাম ফটো দিলে আসি পড়লাম, ফটো তুললাম, ফিঙ্গারপ্রিন্ট দিলাম, বাস
হয়ে গেল।
হ্যাঁ
জি, একদম শান্তি হয়েছে।
হ্যাঁ স্যার।
যাক, ওই কার্ড যেন ব্যবহার করতে না হয়। হ্যাঁ
ঠিক আছে স্যার।
আচ্ছা চলো। now are you getting tired? সবাইকে জিজ্ঞেস করছি, because this is not
No,
very
sir.
soothing part of this course, the standing wave. It's a very complicated thing. You will realize when you will work with the system, when you will really face the problem, then you can find that what is the meaning of standing wave ratio, what is the meaning of reflection, and many other things. Well, you bear with me for next 5 to 10 minutes. So now probably what we started at the beginning, that equation has two parts. So now probably you can understand the significance of these two parts. So these two parts may be sometimes a part of the actual system. So we write it in its natural form. So I'm writing in trigonometric form, not the exponential form. So I want to have my voltage magnitude. So if you look at this expression of this magnitude of the standing wave, it varies from at maximum value কত হতে পারে, minimum value কত হতে পারে, under different conditions. If you apply this condition, you can find it. It is not too difficult. Its maximum voltage is the first term. So in other terms will be 0. That means cos term 0, cos term টা কত হবে, 1 হবে, and sin term will be 0. So it is not a difficult thing under two extreme conditions. And another thing, V mean, it is the minimum voltage. So this is maximum voltage and minimum voltage. This equation helps us in getting the simple expression of maximum voltage and minimum voltage, the magnitude. And then we can find the ratio, the standing wave ratio or depth of this standing wave as V max by V mean. Standing wave টা কতটা গভীর or standing wave টা কতটা serious, that will be determined by this term that is called standing wave ratio. Normally it is called VSWR, voltage standing wave ratio. So it is very important that voltage standing wave ratio is directly related to reflection coefficient and vice versa. So equation 13 is important for you and equally important when you will be getting this equation 14. তুমি যে কোনো একটা মনে রাখো, you will get the other value. So reflection coefficient is related to standing wave ratio, reflection coefficient is related to line impedance and load impedance, and reflection coefficient, and by combining all these things you can find relation between standing wave ratio and impedances. Again, this is true, that is less than 1, and standing wave ratio always will be greater than 1. Its minimum value is 1. That is obvious. Vmax and Vmin, when they are same, then there will be actually no standing wave. That is, the ratio becomes 1. So when S is more than 1, then it is significant for consideration. It's -1. Your standing wave ratio, infinity. খুব খারাপ। That means reflection coefficient magnitude is maximum 1, পুরো signal ফিরে আসছে, and standing wave ratio or voltage standing wave ratio is infinity. This is the worst condition when ZL equal to 0. That means ZL equal to 0 means the load is short. লোডটা কোনো কারণে শর্ট হয়ে গেছে। তো লোড শর্ট হওয়া মানে ইট ইজ এ টোটাল মেস ইন দি লাইন। এই লাইনটা কোনো কাজের হবে। Can you guess? Anyone can tell the standing wave pattern? How does it look like?
Sir, is it like a straight line?
দেখা যাক whether your guess is right or not. I'm showing it graphically. 1, 2, 7 help to determine them. Equation 1, 2, 7 and 8. Anyway, so you can figure it out. আমি কি বললাম, ZL কে 0 করে দিয়েছি নাকি? হ্যাঁ, ZL is 0. So when ZL equal to 0, VZ is like this. না, এটা কি করে হবে? আমি ভুল বলছি মনে হচ্ছে। They help determining them. The physical appearance can be visualized, so that will come later. But 1, 2, 7, 8 help with determining them. No, it is VL, Z not L, everything is there. Well, you just keep a note and you do this exercise. New parameter, that's why it is derived. আরে তোমরা করেছো, লিখছো কি? হ্যালো,
হ্যাঁ স্যার লিখছি।
লিখছো। So এই যে step 1, 2, 7 and 8 taking help all this together, how do I reach this final form? এটা বাড়িতে নিজে নিজে করে দেখো, then you can realize. এই যে আমার সবথেকে সিগনিফিকেন্ট টার্ম এখানে, here it is L minus Z. L minus Z টা কি ছিল? আমরা L প্রাইম ছিল, মনে আছে?
হ্যাঁ স্যার।
Just few steps
Yes, sir.
ago we consider it L prime, কিন্তু এটা L prime থেকেও আমি অন্য একটা প্যারামিটার এখানে ইন্ট্রোডিউস করব এবার, that you need in your practical laboratory next year. So you do this homework and you can find this value. I'm going to next page. Vz equal to this. It is a very general equation. It is very general equation 15. এই আমি ওখানে L প্রাইম দিয়েছিলাম, তো এখান থেকে আমি দিলাম D. D means distance from load end. Distance from load end, এটাকে বলা হয় D. D is the distance from load end. তার মানে এখন আর it is the practical aspect. One engineer, why should this engineer will count L, Z, many parameters? Because আমার ম্যাচিং হলো কি হলো না, I am concerned at the load. আমি লোডে বসে আছি, suppose Kolkata to Shiliguri. So I don't have any need to count L from Kolkata to Shiliguri. The engineer who is sitting at the terminal at Shiliguri, he will just count D, that from this load end where I am going to identify my fault or for all location. That's okay. It is current and voltage relation. So with this equation, we can get three different conditions. আমি আজকে আর continue করবো না because I have a meeting at Jadavpur. So let's the equation up to this and its different conditions we will discuss in our next class. Well, next class is on আজকে কত 8 তারিখ, next class is on
15th.
15th. 15th, I am whole day from the morning I will be busy. You should give me a different slot for this class, preferably in the evening. What about 18th? বৃহস্পতিবার
Yes, sir.
আমার ক্যালেন্ডারে ফাঁকা আছে. It is too
Yes,
tight.
sir.
November, December is too tight for me. বলো.
হ্যাঁ স্যার, ওই দিন আমাদের মানে মর্নিং স্লটটা ফাঁকা আছে আর ইভিনিং স্লটটাও ফাঁকা।
Oh, then morning is the best one. তাহলে 18 থার্সডে আমি করে রাখি।
Okay, sir.
হ্যাঁ স্যার।
তাহলে 18 থার্সডে অর ইভিনিং, তোমরা দুটোই ফাঁকা রেখো, আমার সঙ্গে একজনকে যোগাযোগ রেখো।
আচ্ছা স্যার।
ওকে স্যার।
আমার সঙ্গে তো ইমেইল রয়েছে, তোমার নাম কি? সায়নদী, তাই না?
হ্যাঁ স্যার।
ঠিক আছে, ওকে।
ওকে স্যার।
হ্যাঁ, তুমি নামগুলো আমি পাঠিয়ে দিও। ওকে,
ওকে স্যার।
ফাইন।
হ্যাঁ স্যার।
So I'm closing for today and we'll meet again on 18th, preferably in the morning.
ইয়েস স্যার।
Okay. Take care.
ওকে স্যার।
Thank you, sir.